So as a few of you noticed last week, for whatever reason, the sound wasn't recorded in the YouTube videos. And so, unfortunately, you'll have to go to the week before, or the year before, if you want the audio version. Of course, all the slides and everything are still available, but the lecture itself is probably less useful to watch without any audio. It now seems to be working fine, so hopefully this will work correctly. I've updated the slides from last week on dynamic experiments with a bit more detail and a few more sort of examples on still working, okay, on the process of making these sort of pipelines. And we've updated the exercises as well to include, where is it? Newest. No. This one. To include some more examples of what we do here. Basically there's some new graphs like this to help explain this idea better of where you try to register these images together and sort of what that process looks like and kind of why it's iterative, and sort of as you improve it, you get more information for improving, for changing your metric, and that you can run this hundreds, if not thousands of times before you end up actually getting a convergence. And so when you run the code, it says things like iterations, and this just sort of explains a little bit better what those iterations mean. For the example we did, we had this very basic sort of grid search-based optimizer. We had the transform, which was just using this sort of affine transform with a nearest neighbor interpolator, because you're not always on a perfect grid, and then a mean squared error as a metric. And so our initial image looked like this, our fixed image on the left looked like this, our image we're trying to match to it looked like this on the right. We could then use TensorFlow code to try to align these on top of each other. And so this was an example where we use this sort of affine operation in TensorFlow because it's much more efficient. We then can show the graph for all of this. So for whatever reason. Okay, I think if we go to the handout, it should be easier to see. Yeah, that looks better. But basically, TensorFlow offers this tool called TensorBoard, which allows you to actually look at the graph that you've created. And so you can see that it matches quite well here what we did before. So we have this metric, we have a moving image, we have a fixed image, we apply this transformer to it, and we sort of iterate in this fashion. And so you can open up all of these blocks, and if you're comfortable enough with zooming, look at all the components that sort of go in to this kind of operation. And you're not expected to understand all of these, but this just lets you see easier what's going on in some of these more complicated systems. So you can then run it, and you could watch sort of from a starting point how it moves this image ever so slightly to try to make them overlap better. We can then improve this process further by focusing on just the center region, because as you see here, we get penalized for the fact that there's not an overlap there, so that the error is quite large. And by focusing on this window, we can do a much better job of actually getting them to overlap for whatever reason in this video. You don't immediately see that? Because the gradient isn't very smooth, and so by creating a distance map of the image, rather than the image itself, we get a much smoother gradient, because if you look at the image, you sort of have these gray and sort of darker and whiter regions. If we do a segmentation and create a distance map, then we get sort of smooth surfaces that we can try to overlap. And so by running that again, with the distance map, we see we get a very nice sort of improvement until they overlap perfectly. And so running exactly the same operations, but instead of using the input images, using a distance map of the input images, we get sort of a much clearer convergence when we're trying to perform this registration. And so really the point for this is that you can apply these different techniques, and a lot of times they require a lot of tweaking to get them to work really well. And so in a case like this, you have to sort of think about the region of interest, think about the different operations that are available, and what sort of makes the most sense if you're trying to optimize this. And so with this distance map, you sort of get a constant improvement, because the more they overlap, the better it does, versus if you start off with just the images themselves, it often kind of has to get over this initial part of overlapping okay, where we see that, this spot sort of overlaps fairly well, but the other spots don't. And by using a distance map, we sort of encourage that to happen quicker. You can then use different metrics for this. And so this one uses sort of image similarity instead of mean squared error. And so with image similarity, we can try to use that with just the images itself, because it incorporates more information than just a mean squared error. And that's one of the things we covered in sort of the second lecture, so you can also use that as an optimization criteria. And then we have sort of the simple ITK approaches below. But basically those things have been quite a bit improved and extended so that you have this example implemented in a number of different ways. If you then go to the exercises, there's this X-ray patient scan registration, where we show basically how to do this registration from a patient at different time points. And so here we have 24 scans from the same patient. By looking at this image, it's quite clear that maybe the scanner manufacturer or scanner settings changed between those two, so those probably aren't great ones to try to register, but that for everything else, it works fairly well. And the problem is really that when you look at scan 1 and scan 2, and you take a difference image, you don't see what the actual changes are. You see much more that the image has shifted, the patient's in a slightly different position. And what you really want to see is that, this lung got slightly bigger over there, and that this lung got a little bit smaller, and that, maybe there's a new cable placed. And so if you could register these very well, it would be much easier to do that kind of analysis. So for OpenCV, you can do something called feature mapping, where it tries to find points in both images. And so here it shows you the points it was able to match up using kind of this edge algorithm. You can then see when you try to register it using this technique, it maps those points, and you end up with a very odd registration, because it doesn't have points distributed everywhere in the image, and some of the points clearly get mapped to not exactly the right position. And so when you use these techniques, you need to be very confident that there are enough unique, clear features for this to identify. So this kind of technique is made for images with lots of edges. And so if you look at what it's doing, it has sort of this brute force matcher with a sort of orb feature. And so if you read in more detail about what an orb feature is, it really focuses on edges in the image. And so if you don't have a lot of clear edges or shapes in your images, it makes it much harder. But if you're doing something like registering a piece of paper that you take a picture of, it works very well for that. Simple ITK, you can do this registration. For this, we show sort of a test pattern and a registered test pattern, because it makes it a little bit easier to see what actually was done. And so it sort of rotates and shifts the image a little bit. And that we can look at this post-registration difference, and it looks much better. And so there's many fewer things there. A lot of the artifacts are kind of removed, and so clearly it's an improved registration. We can go one step further, and allowed deformable registration. So we look at all these different sort of sub-regions and register them independently. As we see with this, you can get very crazy registration patterns. And so when we run it, it sort of shifts things around in ways that may not seem so reasonable. And that when we look at the resulting image, that doesn't really look like a human body very much anymore. And so it's gotten this image to match this one better by deforming the lung there so it overlaps, but probably that wasn't the right step to do. The last one, the second to last one is then PyTorch. Has anyone used Torch? Or does anyone use PyTorch? Some? One person? So you can also do these kind of operations with PyTorch, where you basically create this sort of affine transform and you perform this optimization where you can register these two scans on top of each other. So this is the original image. You run this optimization over a couple iterations and you get this result. And so it doesn't transform it very much, and probably we need to use distance map or some other tools to improve this. And that, yeah, you see the result there. TensorFlow, the same kind of thing. But of course, in TensorFlow, it's much more verbose because fewer of these things exist already. But we can sort of give it this image and have it try to optimize it to get better results. So if you're interested, this is a very obviously important problem. Registering X-rays is not solved at all. And so coming up with a good way of finding what are the key differences is very important to work on. And so you can feel free to take these examples and tweak them using whatever approach you're most comfortable with, depending on what community you come from. You're more familiar with tools like ITK or OpenCV or PyTorch or TensorFlow, but they all have very similar tools inside of them. So even the OpenCV approach, which works so poorly here, can be modified. You know, if you do edge enhancement on the image or maybe some contrast enhancement, it'll find more edges, or you can reduce the threshold so it finds more of these patterns to match so that you can get better results. But these are just sort of the first initial results to see how a lot of these different techniques work. So that covers it for the last lecture. We can now go on to sort of the lecture from today. Here it is. The graphics in the slide from last year look better, so we'll use them, but the slides from this year will soon have all of the same graphics as well. So the slides from last year were done in R, which is just a little better suited for statistics kind of analyses, but the content is exactly the same as what's in this year. So the title for this lecture is really about statistics and reproducibility. And the reading material for this has some of the same as we've looked at before, but there's quite a few new specific sections that are more interesting. So for chapter 3, for this morphometry with R book, this is covered quite well. Then there's a number of sort of grammar of graphics is a very helpful book to read for visualizations. Videos, podcasts, articles, even television shows like Last Week Tonight have covered some of these ideas before. And so if you're interested in more engaging versions, there's plenty of those. Then there's a number of sort of papers and websites covering sort of MATLAB tests, visualizing genomic data, databases, for those of you who are interested. And then model evaluation. And so there's some nice articles from Stripe, one of the technical people at this company. So they do credit card transactions and sort of how they build accurate models for identifying fraudulent transactions very quickly. And so they talk about a lot of the issues you run into with this, obviously from a less scientific experiment perspective and a much more pragmatic, we have a real problem to solve experiment. So in terms of what we've covered before, we've covered a number of these topics. We've kind of been able to create a large number of metrics to quantify what's going on in our image. And this lecture is really about how do we extract this meaningful information and start to make useful conclusions from it. And so we kind of looked at last time the fact that, the course is called Quantitative Big Imaging. What does that mean? We haven't really dealt with that much or any big data examples in this class. And so it's really about being ready for big data. And so being scalable, fast, easy to customize, and working in a disciplined manner. And so that's one of the things we'll really cover today, where you have sort of fixed steps, easy to regenerate results, no magic, everything automated and easily sort of adaptable. And so, with scientific studies, the goal really is to try to get a single number that describes kind of every sample you've looked at. And if you go even further than that, the goal of many studies is just to get a p-value or a t-score from your results. And so you want to be able to say the difference between these two groups is significant because the p-value is less than 0.05. And so what we're going to cover today is much less on how we describe the structure well, how we analyze these images, and much more in making sure that the metrics that we extract are meaningful. And so how do we compare numbers from different samples and groups? How do we compare samples, within the same group? How do we ensure that sort of different processing steps like filter choice, minimum volume, resolution sort of don't affect our results too significantly? How do we evaluate the parameters? And how do we ensure sort of our techniques do what they're supposed to do? And then finally, if we have time at the end, we'll cover a bit of how do we visualize so much data and what are some good approaches for doing this. So in terms of kind of the outline, we'll cover a bit of the motivation at the beginning, some of the scientific goals, a bit about reproducibility, prediction, and validation. And so this will fit back well with what we've covered before, with sort of our machine learning approach to image analysis, but focusing more on the results side than the image processing side. Statistical metrics and results, parameterization, which covers sort of a number of sub-issues, unit testing, and then visualization. So I assume everyone has taken a statistics course before. Has anyone never taken a statistics course? And probability courses? Everyone as well, good. And in terms of unit testing, has anyone heard of that before? One person. And if you do it? No. Okay, good. So in terms of what we start with, we have our original kind of cell images or any number of examples that we looked at before. We're able to get rid of noise. We can analyze shape. We can even track cells across multiple frames. We have all kinds of information about this. And now what we want to do is how can we do something meaningful with it? And so one of the important things, this probably has been covered before for most of you, but it's important to reiterate, is this sort of idea with correlation and causation. And so for any of you who've submitted papers, it's one of the most sort of common criticisms you get when you submit a scientific paper is that you sort of confuse correlation and causation. And so you see some statistical results like, the temperature increases bubble size in your foam, and you sort of say that the temperature increase causes the bubble size to grow. And, that will often be criticized with, well, you found a correlation, but that doesn't at all imply that the temperature had anything to do with bubble size. They could just both be happening to change at the same time, or you increase the temperature as the experiment went on, and because of coarsening, the bubble sizes would grow anyways, or any number of other sort of results that you could have out. And so to kind of define these clearly, we have this idea of correlation, and this means that there's sort of a statistical relationship. It's very easy to show. It's a very simple formula. a single calculation to show that two variables are strongly correlated. And causation really implies that there's sort of a mechanism between A and B. And this is very difficult to show and impossible to prove. And so you can see why this is a very easy criticism to make, because you could pretty much make it about any claim that anyone has ever made. And so the important sort of distinction here is that sort of how can you start to make this bridge between just performing statistical analysis and actually having some sort of causative understanding of what's going on. And so one of the important tools that we have in science is this idea of sort of a controlled study. And so we have two broad, yeah?
Why is it impossible to prove?
Well, simply because you can never be 100% sure that one thing caused the other to happen. I mean, even with gravity, it's a theory. Right. That you'll never have a perfect probability. If you drop an apple now and it doesn't fall, it doesn't mean gravity doesn't exist. And if you drop an apple now and it does fall, it doesn't mean gravity exists. It could be that there was a fan above it blowing it down. And so there's never a way to be 100% sure that you've proven something you're trying to do.
But that's basically everywhere in science.
Everywhere, yeah. So in math, you don't run into this problem because you can prove all kinds of things based on axioms. But in science, you can never, because basically the only way to establish causation is to say there is no other possible way it could have happened. And as long as aliens could have a tractor beam from outer space and have made that result look like what you saw, which is unlikely, but not impossible.
That's why you use repeatability. You do it several times to make sure that you can isolate that kind of...
Right. Well, you do repeatability, and you focus on trying to figure out what the other possible reasonable causes would be, and making sure that they're as unlikely as possible.
You don't have to say that there is no other way it could have happened, because they could be multiple causes. It doesn't mean that the one cause is nullified or is invalid.
It doesn't, but if there were something like that going on, I mean, the aliens example is, of course, extreme, but if you say, with the temperature that the bubbles get bigger, there could be a chemical reaction going on inside causing gas to be formed that makes the bubbles get bigger. That is completely independent of temperature. You just happen to see temperature go up and the bubbles get bigger.
Can't you do an experimental setup too? Because you can either observe that or you can actually make an experience to test that hypothesis. Maybe bring the temperature down or see how it
Right.
goes.
And so that's where we get into these ideas of sort of having observational and controlled studies. And so when you have this initial idea like temperature and bubble size are related, you can say, I saw this in one study, it's interesting, now I want to show that there's a causal relationship, and so I try to remove every single other possible factor. So I try it with different chemicals, and the likelihood that there's different chemicals that produce this gas in the same way as the chemicals I used the first time is very low. It's obviously not zero. You could have some weird combination of chemicals that happens to produce the exact same behavior. And so when you look at these things, it's always about sort of ruling out other reasonable explanations, but you can never be 100% sure that you've ruled everything out. Yeah, I mean, you can be very confident. I would say there's very few people who doubt the theory of gravity. But it's still not entirely proven, and there's still parts of it that we don't understand completely. And so, we trusted enough to send airplanes and rocket ships way up into the sky, and so clearly it works fairly well. But to show that we've covered everything is quite difficult. And so you never have absolute certainty that you've ruled everything else out. That with any experiment you do, your plates can be contaminated. You might have, a strong radioactive field in the room that you didn't think to measure. It could be like the experiments we mentioned last week where you were sort of measuring ice cream and you were turning the sugar into formaldehyde, where you would say ice cream crystals change like this with time. And we think that this is a time-based evolution when in fact it's just a chemistry-driven evolution. And of course you could measure chemical samples, but if you don't look for the right chemicals, you probably won't find them. And so knowing that there's really no other explanation is incredibly difficult. And so that's why you sort of run into these problems of you can never completely show causation, but you can have a right approach for you can never prove causation, but you can have the right approach for showing causation. And so that's what we have with sort of this idea of controlled and observational studies, where observational studies is really a lot of what kind of Facebook does, or at least Facebook originally did and Google originally did, where you just kind of explore large data sets looking for trends. So that when you look at what do people make Google searches for every day, does that mean that Superman movies are getting more popular? It's not really hypothesis driven, and this kind of experiment very rarely leads to causation. So if you look at Google searches, it's very easy to find trends in Google searches that have no causative meaning at all. If you examine 100 people and the ones with blue eyes were on average 10 centimeters taller than the ones without blue eyes, you can't saying this means blue eyes makes you taller is absurd. No one would say that. You might have people from Netherlands that you're comparing with people from China, and it's actually many different factors that are causing them to be taller and nothing to do with their blue eyes. That's just a random observation that you've had. 100 cake samples, cooking time, and bubble size, sort of along those lines. But you basically, with these kind of observational studies where you don't really have a hypothesis, where you don't design an experiment, and you just kind of sample random populations, you almost never get to the point where you can really make causation statements. Not that these experiments aren't useful, but they're just very bad at showing causation because you have so little control at what you're doing. I think most of you have probably seen the website before where you have sort of spurious correlations, where you can go on the website and see, I think it's, US spending on space technology and suicides by hanging. And that you see, clearly this is a very strong correlation. And this might actually be based on millions and millions of data points. I can search, I think I found with my biking activity and Google searches for the word Superman, there was a 0.99 correlation. And so, that's an interesting finding. I think with this one, it's 0.9978, but it doesn't mean anything. And if you have a large enough pile of data, there are millions of these kinds of things that you'll find that don't mean anything. And so it's more about being able to identify, this could be an interesting hypothesis. How can I build a controlled experiment to show that there's actually a link between drowning in a pool and Nicolas Cage movies? Which would be quite difficult, but maybe if you had the Netflix data of people who drowned in pools, you could see if they'd watched a Nicolas Cage movie and then maybe start to establish a mechanism. But for these kinds of things, particularly in sort of our society today, where there are such huge amounts of data available, it's incredibly easy to make these kind of curves that don't mean anything. And of course, with this website, it's quite nice because it's obvious for anyone that there's no relationship between spending on space and suicides by hanging. But if you're looking at your experimental data, it might be very easy to say, oh, these things could be linked because maybe temperature is causing the bubbles to get bigger. And you'll come up with a good explanation, and then you'll sort of be like, okay, this is done, when in fact you discovered something as meaningless as that. And what we found very often, at least during my PhD, is that you would make a graph like this. You'd go to your advisor and ask him about it. He would come up with an explanation. You'd then come back a day later and realize that actually the sign was incorrect, that the correlation was the opposite of what you said it was. And he would come up with another explanation that made up just as much sense for why that would be true as well. And so that's kind of the same sort of principle where, if you're dealing with something where it's obvious that they're not linked at all, it's very easy to say, this is nonsense. But when you're looking at something like bubble size and temperature, where you could come up with a good reason for why temperature makes bigger bubbles. The air inside the bubbles move faster. That makes the bubbles bigger. I mean, it makes a lot of sense. But you could probably also come up with reasons why it would make it smaller. And so you need to have this sort of skepticism about these observations and appreciate that they are just observations and they're great for making hypotheses, but they're very bad at sort of showing correlation. So this is where the controlled studies come in, and this is where sort of most scientific studies fall. And this is where you kind of build experiments, where you say, we're interested in knowing more about, is there a link between blue eyes and height? And so we want to come up with, what's the right sampling strategy for getting people recruited into our study? How do we accurately measure their height? What else do we need to measure that might be a reasonable cause for them being taller? Are there other factors that come in? And this is where you can start to lead to causation. And so it's where you really make a much bigger effort to control the settings that you're looking at. You're often dealing now with much smaller data sets. If you have to recruit people into a study, that takes much more time. This 100 cake samples, you'd have to think about what else could be causing the bubbles to get larger that you'd want to rule out. Maybe decreasing the temperature and see if they get smaller, or, changing the chemicals, or changing the environment, or changing the pressure. Could all be things you could do to show that this link actually existed. And that this, we examined 50 mice with gene XYZ off, and 50 mice with gene XYZ on, and we saw that the foot size was increased by 10%. And so that is a much more controlled study where you're able maybe not to entirely show the causation, but you're able to make a much stronger link than if you just look at millions of mice with millions of different genes on and off and say there appears to be a correlation. So in terms of kind of a simple model, or the basic one that's very frequently used, is this idea of sort of a magic or a weighted coin. And the question that kind of comes up, and I find this very comforting because this shows up on Google interview questions. So if you want to get a job working on data analysis at Google, you need to be able to have good answers to the questions that show up on these slides. That you buy a coin at a shop, and you'd expect a coin that you normally buy to have a 50% chance of being heads and a 50% chance of being tails. And so, how many times do you need to flip the coin to prove that it's not fair, or prove that it is fair?
I guess you have to set a certain value of confidence.
Yeah.
And then you would run an experiment, like run a series, number of trials that could match the kind of confidence.
Yeah.
And if your result shows that this could only happen in accident that has such small probability that it goes below what you set as threshold, then you would assume that the coin is biased.
Yeah. So basically, the answer to the first question is you can never prove it's fair or not fair. If you flip it 100 times and it's heads every time, that's a very, very unlikely event. But it doesn't mean your coin isn't fair. It could happen. And if enough people flip enough coins long enough, eventually you'll actually see that happen. It's not impossible. It's also not necessarily. I think it's inevitable if you do it forever. but that's less relevant. But you basically can't ever say that this is fair or this is unfair. You always deal with sort of a probabilistic mentality of this is my cutoff for being fair, and this is what experiment I need to do in order to show that it's at or below this cutoff. And so then you kind of have questions like, if I flip it 10 times and another person flips it 10 times, is that the same as 20 flips? Yeah?
Doesn't it depend on your control standard in general?
Yeah.
What do we say it's a variable you want to consider?
Yeah, so it's, if you assume both people are equally unbiased flippers, then it's fine. But if one person's flipping the coin in sort of a very odd way, then that doesn't represent a reasonable sampling of the coin. Yeah. This is obviously the most horrific thing that you see. If I flip it 10 times and then multiply the results by 10, is that the same as 100 flips? So the answer should be fairly easy, but the why is quite a bit more difficult.
It's not the same.
It's not the same, yeah? Yeah?
The idea of flipping the coin is that every event should be independent, but if you multiply the results by 10, then you're repeating a bunch of measurements, so they're no longer purely independent from each other.
Exactly. So you basically break this idea of independence because you don't have, each one of those 100 events is not independent. That only 10 of those events are independent, and the other ones are all completely 100% dependent on what happened before. And that this is the kind of problem that, the mortgage or banking crisis a few years ago was fundamentally caused by, that people assumed events like defaulting on your mortgage had a much higher degree of independence than they did. And of course, if you flip a coin once and multiply it by 1,000, it's, quite clear that you would get a seemingly incredibly rare result because you got 1,000 heads in a row, when in fact that's, a very common event because it either had to be heads or tails. And then sort of, if you buy 10 coins, the more experimental side, and you want to know which ones are fair, what do you do? So this is where you certainly, if you've taken statistics or probability classes, you've run into this before. The act of performing a coin flip is this fancy F, and you have sort of this observation G, I think, of I, which represents one flip. So if you have a fair coin, that doesn't mean you'll get exactly half heads and half tails. It means that the expected value is 0.5, so that you would expect on average to get half heads, half tails. And sort of an unbiased flipper was this idea of, if you have, two people flipping coins, that, their flips are sort of independent of the other ones, and the flipping process itself isn't changing the observation, that it's just sort of random in itself. And so if you look at kind of what's the expected value of the flip, you have to perform kind of an infinite number of flips in order to ultimately reach that 0.5 value that we show there. And so for any single given flip, it doesn't really mean anything. It only means something on sort of the grand scale. And so the way to kind of think about it is that, each flip gives us a small piece of information about the flipper and the coin. And that more flips provide us with more information. So this is sort of the Bayesian approach to dealing with these kinds of problems, is that rather than worrying, Bayesian of course deals with a lot of math as well, but just from the perspective, rather than worrying about the math, just think about what are you actually gathering. That, if you think about what information you're getting out of your system, each flip is giving you a small piece of information, More flips provide more information, and by that sort of rationale, multiplying flips by 10 provides you with no new information at all. You have exactly the same amount of information you had before you multiplied it by 10. And so you're not gaining any insight into what's going on. And the idea here is that sort of random and stochastic variations in the coin and the flipper cancel out. So that your flipper is random enough and that your coin is random enough that any of these variations disappear. And the only thing that sort of accumulate would be systematic variations. And so if you had a biased coin, that would be something that wouldn't cancel out over 10 or 20 flips. That would be something that you would see accumulating over a large number of experiments. So when we translate this to kind of the real experiment world, you know, each measurement tells us something about our sample, our instruments, and our analysis, and that more measurements provide more information. So the random and stochastic variations in samples, instruments cancel out, and you know, the analysis should have very little stochastic variation or random variation, but the systematic variations accumulate. And so this is where you'll often have in your analysis that systematic differences will start to grow and sort of increase with time. So I think I'll take a break here, unless there's any questions on this so far. No? Okay, so we'll take a break.